So I hope that you can get some benefit out of these 2 extra sessions. And good luck with your end semester test. Synchronous machine, this will be the last content or topic of this course. So there are 2 lectures on synchronous machines. I am covering part of it today, and then Dr. Nuantha will do the rest in the week after next week. So that will be week 13, is it? So firstly, the content or objective of this lecture, that you get familiar with the construction and operation of synchronous machines. And particularly we will look at some of the aspects of synchronous machines, that why the number of poles has been chosen. What are the determining factors for choosing the number of poles in synchronous machines? What are the different types of synchronous machines? And what is synchronous speed? And the big question is, why the name of this machine is synchronous machine? That is interesting and important to understand why they are called synchronous machine. Because the word synchronous we use in many other places as well. Even in induction motor there is something called synchronous speed. So why this machine is known as synchronous machine? In this course, if you want, not in this course, in this lecture, on the topic of synchronous machine, if you want to understand one thing, that is why the name synchronous machine. If you understand that, that is enough, I think. Why it is called synchronous machine. Then we will be able to draw the equivalent circuit of synchronous machine, and as you have came across throughout the course, that for single phase transformer, 3-phase transformer, DC machine, then induction machine, all of those, we actually represent the electromechanical operation or interactions by using a simple electrical circuit with the combination of resistance, inductance and capacitance, voltage and current. So these are equivalent circuit. So we will have a similar equivalent circuit for synchronous machine. Equivalent circuit is an electrical representation of the complex electromechanical interaction within these machines. So all of these you have seen, there are a lot of flux and many stuff. But when you come to an electrical circuit, there is only voltage and current and resistance. So equivalent circuit is like electrical representation, and there are many assumptions when we represent an equivalent circuit. When you study synchronous machine, one of the important concepts is synchronous reactance. And what is that? Synchronous reactance. I have looked through roughly at least 3 of the tutorial questions in tutorial 7, which is on synchronous machine. At least the first 3 tutorial questions, that is asking you to determine the synchronous reactance, or given the synchronous reactance, they ask you to determine something else. So synchronous reactance is an important concept in synchronous machine. Just remember that. Then we will be able to draw the phasor diagram of synchronous machines, and we will practice a little bit in the class. When I marked the mid-semester test, when we marked the mid-semester test, then we see that there is hardly any student who got marks in this equivalent circuit part. Sorry, the phasor diagram part. So there are only few. So the phasor diagram, you know that it will come in the exam, and you will not answer that. So I don't want that to happen. I want to make sure that the phasor diagram, they will ask you to draw in the exam, and you will draw it correctly. So we will practice a little bit. Phasor diagram of synchronous machines. So there are sort of 4 contents actually. Construction and operation of the machine, equivalent circuit, synchronous reactance, and phasor diagram. So to start with, I think I told you before as well, all of these individual components or topics in this course is actually, you don't see that much similarity. Or even you see some similarity, you get confused. That, I mean, in terms of equivalent circuit or in terms of phasor diagram, you mix with each other. So all of the contents of this course, which are individual, all are actually joined together or combined together in electrical power system. Each of these components has been used in electrical power network. So, and synchronous machine is actually serving us for over hundreds of years. So whatever electricity we consume, that are coming from synchronous generators. So majority of electrical power is coming from large generators, irrespective of the fuel type. It doesn't matter, it is coal, gas, nuclear, or hydro. All are running large synchronous generators, and they are producing in the range of thousands of megawatts of power. Only recently, maybe over the last 20-30 years, the proportion of renewable is increasing, and there is wind generators, which are induction generators. But still, they produce in the range of a couple of megawatts. On the other hand, synchronous generators, thousands of megawatts. So synchronous generator is actually supplying the electricity to the grid. In Australia, anyone knows what is the penetration of renewable? How much proportion is coming from solar and wind? Rough idea?
6 or 8%.
So installed capacity around 15%, but actually, as you know, those are weather dependent, so the penetration or actual generation is around 5-6%. So still majority of the power is coming from 90 to 95% is coming from synchronous generators. So that is very important. Now, this is a synchronous generator that stays within a power system. So just a little bit, this is not the main focus of our lecture. So like there is a turbine, or they call prime mover, that is actually rotating, and that is running the synchronous generator. And for these synchronous generators, depending on the network demand, sometimes you have to speed it up, you have to supply more fuel, sometimes you have to slow it down and you give less fuel. And those power controls are coming from the governor, and governor is asking to the bulb whether you need more fuel or less. So this is the synchronous generator, what is staying here in the network. And then you are supplying this power through the step-up transformer to the rest of the network. So this is just a visual representation in a power system where synchronous generator is sitting, and there are different types of controller. So there is a governor, which is an essential part of generation control, and here it is called AVR, automatic voltage regulator. I think you will study some of these in advanced power system or some other courses. AVR and governor, which is sitting there. So these two are controlling the synchronous generator voltage and frequency and operation and power, everything. So as we have mentioned, in synchronous generator, they are producing actually very large amount of power in the range of thousands of megawatts. So they are also very big in size. Maybe one synchronous generator like the size bigger than this room. So there are some people standing there, and this is your synchronous generators. So this is just showing you the size of the machine. And one person is working here, and this is the size of the machine. And there are different technology, air-cooled, hydrogen-cooled, all of those. So this is one of the synchronous generator repairing work is going on. So what we see on the outside, that is the stator, isn't it? That is the stator. And inside this, in the middle, there are rotors. What are actually these? So these are showing the rotors of the synchronous machines. These are very big, very, very big. So if we want to look at it, the construction of a synchronous machine or synchronous generator, on the outside there is a stator and inside there is a rotor. And what happens in the rotor, that there is a DC supply coming into the rotor. A DC supply is coming into the rotor, and that DC supply, because there is electricity flow, it is creating a magnetic field. And then this rotor is rotating externally by using prime mover. Then when the magnetic field is rotating, you have conductors here. Then when the rotating magnetic field is crossing the conductors, there is voltage induced in these conductors. And from these conductors, you are taking out your electricity. We will explain a little bit more of this concept. I think understanding this is very important for this course. And let's go back to the old days for a while. So this one, this is an iron core. And what we will do, we will put a DC supply there from an external. Is it better now? A little bit better. Yeah. So let's say there is a battery, DC source, and this DC winding, we will put it there. So once you give some supply voltage there, there will be current flow, and due to this current flow, there will be a magnetic field. So, and the magnetic field is coming out through this way and entering into this way. So let's say this is North Pole and this is South Pole. And this is just basic. What we will do, we will use this solenoid or magnetic field as the rotor of our synchronous machine. And then we will put outside here a stator and in that stator we will have some conductors. Let's say a bunch of conductors here. And I am saying that this is my phase A, conductors. It can be any conductors, just conductor. Now, there is a magnetic field. By some external force, using prime mover or turbine, what I will do, I will rotate this magnetic field or this rotor. So this is our rotor, and outside that is our stator. Now what I will do, I will try to rotate this magnetic field. Once it's trying to rotate, at some point, after rotating, this solenoid or this rotor will be like this. If it is like this, then my north pole is here and south pole is here, and my magnetic flux is going through this way. So what is happening from this operation is that I have a magnetic field which is crossing a bunch of conductors. So due to this magnetic field, magnetic flux, there will be an induced voltage. There will be an induced voltage in these conductors. Now if we look at the intensity of the magnetic field or magnetic flux, considering that I am sitting here. So when your rotor is in this direction, there is very low magnetic flux, so the induced voltage will be very low. As this rotor is moving towards the conductor, the flux or the induced voltage magnitude is increasing, and that will be maximum when that is facing towards the magnetic field. Then it keeps rotating and the magnetic flux intensity is decreasing. It keeps moving. At some point the north pole is in this side, south pole is on that side, and then south is approaching towards this conductor. So a negative flux compared to north, south will be negative. Then when south is here, it reaches to the negative peak, and as long as the rotor is keep rotating, it is coming back like this way and continuing this way. So what is the mechanism here? We have a DC supply in the rotor. That rotor is creating a magnetic field, and by some external force we are rotating this magnetic field, and this magnetic field is crossing my conductor which I put on the stator. Due to this rotating magnetic field, a voltage is induced in my conductor, and that is I am collecting to supply to my power system. So this is one of the conductor set. If you put another conductor set here and you name it as phase B, another set of conductor here, you name it at phase C, then you get three-phase supply. And as you can see that this north pole, once approaching here, it will come here after it crosses 120 degree. That is actually the phase shift between phase A and phase B and phase C. Easy? Or is it okay? Now, there is one more interesting fact here. The most interesting fact is that every time this rotating magnetic field or rotor, every time this rotor is passing this conductor A, every time it is passing a conductor A, this is completing one cycle. Am I right? That's why the frequency of the generated voltage is governed, is led by the speed of this rotor. So from where the word synchronous comes, that the electrical frequency is synchronized with the mechanical speed of the rotor. Electrical frequency is synchronized with the mechanical speed of the rotor. Every time your mechanical speed finish one rotation, your electricity finish one rotation. Every time, okay? So, one simple question. Whatever I have drawn here, how many poles are there? I make it simple. What is the value of P? You see P, pole. No, P doesn't mean power here. P is the pole, number of poles. You have seen that in some other mathematical problems, tutorial questions. My question is, what is the value of P, pole here? What we have considered here? 2. And how many pole pairs? 1. So make sure that you are happy about that. There are 2 poles actually here. One north, one south. So the value of P is 2, but if you say pole pair, there will be 1. Okay? We will see later that the electrical frequency, Fe, and the rotation of this machine, mechanical rotation, that is actually they express is Fm. Better. So electrical frequency and mechanical rotation, they are actually related by the pole. In this case, so you will see later an equation, Fe equal P over 2 Fm. In this case, Fe is Fm is the same because we have 2 poles here. Okay? So we have seen that every time it finishes one rotation, I have one frequency, like one complete cycle, isn't it? So if you have 1 pole, then you are doing 1 complete rotation, 1 electrical full cycle is done. Okay? Now, it is a bit of a mess, isn't it? If I want to draw something else on this. Okay, I am not going to draw something else on this. I am drawing a new one. Now, just to recap this idea, because this idea is important. Throughout the whole synchronous machine, if you just remember this part, I think that is a good understanding of synchronous machine. Then the mathematics, you know, equation is given in the question, so you can solve mathematical problem. That is not a big issue. The understanding is important. So, in synchronous machine, you supply your rotor through a DC source, a magnetic field is created, and then your rotor you rotate by using prime mover, by some external force. Okay? So in case of hydro power generation, you let your water down from the hill, then you put a turbine there, so and you use that mechanical energy to rotate your rotor. And your rotor is already supplied by a DC source, so that is already creating a magnetic field. And when this magnetic field is moving, then there is a conductor, you get the induced voltage from these conductors. So this is the mechanism of power generation from a synchronous machine. Why the name synchronous? Because electrical frequency is dependent on the mechanical frequency or rotation of the machine. So every time you have one mechanical rotation, you have one electrical frequency, electrical cycle. Now, the world is not that simple. It is complex and complicated. I think you experience that throughout your life so far. Now, we have more. There is only one pole. If the number of poles is more, so I have one north and south here, and I have another, oh, I'm hiding something from you. Another north and south here. So this is a 4-pole machine, means 2 pole pairs. And similarly, you will have magnetic field and DC supply. So I am just ignoring that part. Now you have DC supply and everything. So now you have a stator. And similarly, you have your phase A, phase B, and phase C. They are not one conductor, there are actually many. A lot of conductors here actually. Maybe thousands of turns. Now, if we are sitting here at A, what I see that a north passed me, and so this should be, I think, like this. Oh, is it? North, south, what I'm doing here. Because there should be, after north, south will come, then north will come, then south will come. So we will give supply in that way. So what will happen if there are 4 poles? You see one north, and you see one south, then you see one north, then you see one south. So what I am saying, if here it was 2-pole machine, and this is a 4-pole machine, so if a 2-pole machine and 4-pole machine is rotating at the same speed, your generated frequency will get double, because by the time your north pole and south pole passes this one twice, and this generated frequency is dependent upon the number of poles and the speed of the machine. Bit confused? Oh, it's fine. Let's do a little bit of more here. So as we said that our electrical frequency, that is actually related to mechanical frequency or rotation, and by the pole pair, the relation is with the pole pair. If there is one pole pair, means 2 poles, then they are the same. But if there are 4 poles, means 2 pole pairs, then you see that the frequency is double. Let's see. What happens for this one? I have 4 poles, means 2 pole pairs. So in this case, my electrical frequency will be twice the mechanical frequency. Means my 2 pole finishes 1 rotation, but my electrical frequency, it sees 2 north, 2 south, so there will be 2 positive and 2 negatives. Does it make sense? Now, again, here, F electrical, P over 2, Fm. You are happy with this equation up to now, isn't it? Good. If you are confused, just tell me. Now, P over 2 is fine. Fm means that is revolution per second, isn't it? Because this is related to this electrical frequency, which is hertz. So if this is revolution per second, how can I convert into revolution per minute? So if the rotational speed of my machine is n, for example, and I divide that by 60, so this was per second. Once I divide by 60, it will be revolution per minute, isn't it? So in that case, my n, that is in RPM. Just remember that. My n is in RPM. I haven't done anything here. Just converted revolution per second to revolution per minute. Okay? Then what you get, you see, you got actually P and N, number of pole, revolution per minute of your machine divided by 120. Have you seen this equation somewhere? So, like electrical frequency, I think even in induction motor you have used this equation for the synchronous speed. Omega S, synchronous speed was this. Now, when we consider this type of rotor, for simplicity, for easy understanding, we have shown that this will create a sinusoidal wave. But you can see there are huge flux intensity here, but there is some sort of gap. And again, huge flux intensity there. So it is usually doesn't generate this smooth sinusoidal form. Rather, what it generates maybe step by step. So positive, negative, something like that. The number of poles you increase, the smoother will be your voltage production or flux. The smoother will be the flux density or magnetic field, and the smoother will be your voltage. So we have to increase this number of poles in the machine. But what you can see in this equation that is very interesting, our electrical frequency, we want it constant. What is the operational electrical frequency in Australia? 50? Good. I thought it is 60. 60 is in USA, is it? Yeah. Sometimes we got confused because we follow the books written by US writers, and in all of the questions, the frequency is given at 60 Hertz. So we forget that our country is operating at 50 Hertz. Anyway, so we want this to be fixed, 50 Hertz. Now, as you increase the number of poles to smooth out your voltage, you have to reduce the speed of your machine. Because electrical frequency has to be constant, isn't it? So this too is actually playing an opposite game when it comes to frequency. The higher the number of poles, the slower the machine will be. Because you can't change 50, you can't change 120. It is their relationship. So the faster machine will have low number of poles, the slower machine has to be higher number of poles. Now how do we choose that? What type of machine? Yes?
I was just wondering, in real life situations, is the weight delayed
Say it again.
Like, in real life situations, if you have more poles, would that slow it down in the weight?
If we have more number of poles, then
Would the
weight of the
increase the speed? So you have to factor that in? Or?
It would just increase the rotational motion. So the torque of the prime mover would...
The prime mover has to be like more powerful or less powerful, because you have to rotate torque. Yeah, you have to rotate that to get this speed anyway. Because we are just coming from very basic theory. If you want to buy a synchronous machine today from any manufacturers, because the number of poles you can't just increase or decrease. The machine you buy, it has to have a certain number of poles. You can't just add or remove it, isn't it? Because that is constructed. So depending on the number of poles we buy from the manufacturers, then it will operate with a certain speed as well, because we have to supply a constant frequency. Now the whole set will come together actually, that how strong your prime mover has to be to rotate that machine. But as you are increasing the size of the machine or number of poles, definitely it will be heavier, or all of those issues will come anyway. So in synchronous machine, as we have seen that a rotating magnetic field of the rotor, a pole, can induce the voltage, and there can be more poles. When we look at this concept of poles, like, I have to write again, like this is my stator and this is our rotor, and the rotor is just creating a magnetic field. This type of rotor is called salient pole rotor. Salient pole. Now, what we want actually, that's what we said, that we want this magnetic field, what is created here, to be actually symmetrical or smooth for the induced voltage. So this is the stator. What they do, they create a rotor like this, and they put slots all over the places, and all over these places, because how do we create this magnetic field here? By supplying a DC source through some conductors. So what you do, you pass your conductors through these slots. A cross means positive DC side, this means negative DC side. So what you do, and these are called round rotor synchronous machine. So what we see here, that depending on the operating principle of synchronous machines, the construction can be of two types: salient pole synchronous machine or round rotor synchronous machine. The basic principle remains the same. You create a magnetic field in the rotor by supplying a DC. It is just, they differ just how do you rearrange your conductors into the rotor. Yes?
In real-life applications, what do you see more of? Do you see more of the round rotor configuration?
That is definitely a good question. Let's wait a little bit. We will answer that question. So what we see in a round rotor machine, irrespective of any cross section, the magnetic flux is symmetrical. That's how it creates a sinusoidal wave. If you see here, the magnetic field intensity is very high here, and magnetic field intensity is very low there. And why people use this machine? There is some advantage. Okay, we will go through those. So just I am introducing now that there are two types of these exist: salient pole synchronous machine and round rotor synchronous machine. The magnetic flux is symmetrical. Here it is not. Because each of these has many issues actually. Construction cost, the material, then you have to think about the rotation. Because there are so many poles, the speed can be lower. There are only two poles. To supply the same frequency, you have to give, or maybe you have to put thousands of those to make it symmetrical. What else I want to tell you at this stage? I think this is fine for basic understanding of synchronous machines. Now, based on this understanding, we will go forward with our slides now. So after that discussion, I think once we go through the PowerPoint slides now, you will be able to understand it better, whatever we will say now. So now we understand that DC supply comes to the rotor. And what type of rotor is this? Salient pole. And there are, you can count how many poles are there, then divide by 2, that is the number of pole pairs. And you see the armature on the outside, and they are taking 3-phase supply output from there. Now, after this discussion, I think it makes sense now that what we see there. I have just given you some slides so that you can revise later that why it is called synchronous. Synchronous, it is synchronous because electrical frequency that is produced is locked with the mechanical rate of rotation of the generator, and our FE, electrical frequency, will be the pole pair multiplied by the mechanical frequency, and then that pole pair that is per second, we convert it to per minute by dividing 60 here. Then it gives us this equation, what we have seen before as well. Excuse me. But now I think it is easy to remember for you and understand this equation. The relationship between pole and speed of the machine with the electrical frequency. So remember this, why it is synchronous. Is there more slides after, or we should finish our lecture? Okay, there is some more. Synchronous generator operation, it is the same thing, what we have discussed. In synchronous generator, DC current is applied to rotor winding, and that is producing rotor magnetic field. The rotor is turned by a prime mover, producing a rotating magnetic field. The rotating magnetic field produces 3 phase sets of voltages within the stator. And in this case, we called armature winding, that is the stator outside, and field winding is the rotor inside. So field windings are the windings producing the main magnetic field. Armature windings is the winding where the voltage is induced. So this is just more clarification of what we have discussed so far. Easy. So this is the rotor field we have shown before. For your revision, DC voltage is supplied to the rotor that creates a magnetic field, and rotor flux rotates and creates the induced voltage in the stator. Then synchronous generators, we have that there are 2 types, round rotor machines and salient pole machines. So the round rotor machines, their speed can be very high, 3000 RPM up to that, and salient pole machines, because these are sort of practical, which is possible using the material, using the structure they produce those. And the 2 winding, we say rotor field, that is DC current, but stator is producing AC current. That is also interesting. In the rotor, you are supplying a DC current, but from the stator, you are collecting an AC current. Because you use your prime mover or turbine to rotate that magnetic field. Now, we covered that actually a little bit. The number of poles in a synchronous machine generators depends upon the speed of the rotation and the electrical frequency we wish to produce. So we have seen that in this equation. Where is the equation? Here, that the electrical frequency that is related to the pole of the machine and the speed of the machine. So the pole of the machine is connected to the speed and the frequency. This one for your reference, so that you can revise it later. For example, a stator conductor, stator conductor is fixed. Stator is fixed, that's why it's named stator. It is fixed. What is happening? The rotor north and south is just continuously touching it or passing through it. So if positive voltage is induced when N pole is sweeps across the conductor, the negative voltage will be induced when south pole is coming. So this is the mechanism, and every time a complete pair of poles across the conductor, the induced voltage goes through a complete cycle. We have discussed that, and this is giving us this equation. Now this makes sense, I think. So the number of poles in synchronous machine, electrical frequency is constant throughout the whole power system. Hence, a machine with low number of poles will run at high speed. Now, there was a question that what type of machine, round, rotor, or salient pole, or so you will get some idea that steam turbines are most efficient when rotating at very high speed. Steam turbines are efficient when rotating at high speed. So to generate, again, this is a reference from USA. So to generate 60 Hz, they are usually rotating at 3,600 RPM. So that depends on what type of turbine you are using. Because they are efficient at high speed, so you run this turbine at high speed. Once you run them at high speed, the pole has to be low. On the other hand, hydro turbines, they are efficient when rotating at low speeds. Because if anyone do a mechanical engineering course, so they have at least 2-3 courses on turbine design. How do you really design a turbine? Electrical machines. So efficiency of those turbine and turbine design. So hydro turbines are most efficient when rotating at low speed. If it is rotating at low speed, then the number of poles has to be more. So therefore they usually have many poles in hydro turbine or this type of power systems. Oh. Let's try to solve this problem. There is a hydraulic turbine that is turning at 200 RPM and is connected to a synchronous generator. If the induced voltage has a frequency of 60 Hz, how many poles does the rotor have? What is the answer? Does anyone know the answer? RPM and then F 60 Hz. 36 P is 36, is it? So 18 pole pairs. Is it? 18 pole pair or 36 poles. So if we know that frequency is NP over 120, so if the speed is 200 RPM and the frequency is 60 Hz, then the number of poles you can get from this equation, there will be 36 poles or 18 pole pairs. So lower the speed, higher the number of poles. This is an easy one. What will happen if we have 400 RPM? So previously it was 200, now it is 400. So it means you double the speed of your generator or machine, then the number of poles will be half. This is easy. This is not tough. But that will depend again on the manufacturers, that what is available, what is your requirement, and all of those. Because different capacity machine should have different characteristics. Based on that, it will be decided. So these are the, how do you choose number of poles in your synchronous machine? That will depend how fast it or how slow it will operate, or what is the application, where you will use that. Is this a steam turbine or is this a hydro turbine? So depending on that, it will be decided. So this is the selection of the number of poles. Then we have discussed or covered a little bit this part as well, round rotor versus salient pole. So round rotor, the flux distribution is symmetrical. So they are also called cylindrical as well, cylindrical. And the generated waveform is sinusoidal. Salient pole generators, this is a little bit of extra information. You don't need that because we don't cover damper concept, but I'm telling you the main idea because there is high density of flux and there is a huge air gap. So when it rotates, it see magnetic field, then slow. Magnetic field slow. So there is a damping or oscillation. So for that, there are some extra windings is used. That is another information, but understanding two types, their construction and a little bit of operation should be fine. You have done induction motor before. Now you are learning synchronous generators. So the difference between these two is synchronous motor runs at synchronous speed, and the induction motor, you see there is a difference between the induction motor synchronous speed and the rotor speed, and that is governed by slip of induction motor, isn't it? Remember the definition of slip? That is the rotating speed of the synchronous rotating speed of the magnetic field with respect to the related to the rotor, isn't it? W omega s minus omega r over omega s. So the slip is the difference in the speed of the magnetic field and the mechanical rotation. But in synchronous machine, the rotor is rotating at the synchronous speed. So just remember that difference between these two. Excuse me. Now, so this is the representation of a three-phase synchronous machine in a power system. So this box, this is actually your machine, synchronous machine. So what we have drawn in the circle, that was the mechanical structure. If you want to represent electrically, it will look like this in the equivalent circuit. So we have drawn three-phase A, B, C voltages. So these are generated voltages in the machine, E naught. And as we have seen that the magnetic flux is passing or going after 120 degree, because there are three phases, altogether 360, so they are 120 degree apart from each other in your mechanical structure. So that 120 degree phase shift you see here. So if we want to represent our synchronous machine electrically, there are three phases. Each phases is generating a voltage, E naught, and they are 120 degree apart from each other. And what you see here, the magnetic field of your rotor. And because your stator, outside structure, there are a lot of conductors. And when these conductors is feeding by magnetic field, so there is induced voltage or induction effect. That's what you see here, that because those are conductors or inductors. So that is representing the inductance of your machine, XS. So that inductance, inductor in the stator winding is represented by XS, and this is called synchronous reactance of your synchronous generator. This XS. As you can think about any inductor or conductor, even in a transformer, when you have a many turns of conductors, you know that inherently they will have some resistance and some inductance. If there is a coil, many turns of the conductor, it will have some resistance and some inductance. That's what we see in each of the branches of our synchronous generation, each of the phases, R and XS. Now, you also know that the electrical power loss happens, real power loss happens in R. Real power loss, I square R. So, to minimize the loss, we choose such conductors where the resistance is very low. Especially here, it is a big generators. So the conductor resistance is chosen to be very, very, very low, so that you can supply more power. And particularly in these generator cases, later if you go through some of the mathematical problems or some data sheet, you will see that the resistance of this machine is 100 times lower than the inductance. So you see R and XS here. Sorry. R and XS, your R is much, much smaller than XS. How much smaller? It could be 100 times smaller. Very, very small. It is so small that usually in generators, in synchronous generator, we will neglect the effect of R here. And we will represent this part only by XS. We will neglect R. Unless we want to calculate the efficiency or the heat impact of the machine. Generally, we neglect resistance in synchronous machine representation. And the reason is that is very, very small, and that is practical reason because the conductor is chosen so that the resistance is very, very negligible. And this reactance, that is an important characteristic of synchronous machine, and this is called synchronous reactance, XS. And what we see here, this is a three-phase system. All of the voltage magnitudes are the same. If you connect that to a balanced three-phase load, this is Y connected, Y connected. For simplicity in our discussion, we can convert this type of circuit in per phase equivalent. So we will just consider one phase. That is possible. That we will do in later stage. But now for the time being, we have three-phase generator connected to a three-phase load. Generator voltages are the same, just 120 degree apart from each other. Our load is Y connected and balanced. In this case, our three-phase generator is feeding to a balanced load. The generator is driven by a turbine, what we know, we have discussed before, and it is excited by a DC current Ix. Now, this is again some overview of the previous discussion, that the field carries exciting current which produces the flux. As the field revolves, the flux induces in the stator and creates three equal voltage of 120 degree out of phase. That is fine. And each phase of the stator winding has resistance and a certain inductance. That is for practical reason. And this inductance in each phase, that is creating a reactance. So this is again the basic definition of reactance, 2 pi FL. And this is called the synchronous reactance. And synchronous reactance is a generator, is an internal impedance, same as internal resistance. Now the last line, the value of XS is typically 10 to 100 times higher than the resistance value. So usually R is neglected, unless you are interested about the efficiency or heating effects. Good. We are good up to this, isn't it? Now, what we have seen here, if you just take one phase, as we have said that we will use just one phase, then what will remain? You will have a voltage source, you will have a resistance and reactance in parallel, then you will have load, then you connect through this neutral line. If we want to consider just a single phase. Again, we said that the resistance is negligible, so we will just delete this resistance as well. So what you will have in your induction machine synchronous machine equivalent circuit per phase. In your synchronous generator per phase equivalent circuit, you will have one voltage source, synchronous reactance, and the load which it is connected to. So let's see, per phase equivalent circuit of a synchronous machine. You have a voltage source where induced voltage will come from the rotor magnetic field. You have synchronous reactance and you have a load connected there. Remember, we have neglected the resistance of the machine. In some cases, if the resistance value is given, you may need to consider that. But usually that is too low that we usually ignore that. So this is the per phase equivalent circuit of a synchronous generator connected to a load. The internal voltage of the generator is E0, that is the generated voltage. Then in the synchronous reactance, there is a voltage drop. That's why the voltage at the load end is different than the generated voltage. So the voltage at the load end is E. If we write Kirchhoff's voltage law, that will give us E0 equal E plus I is the current, J XS. Am I right? If we write an equation, the voltage drop here is IXS and voltage here is E. So if I add E plus JIXS, that will give me this voltage E0. So that is the relationship between the internal generator voltage and the load voltage. By neglecting the resistance of the winding, per phase equivalent circuit of the synchronous generator can be obtained. So we neglected the resistance here. In this circuit, the exciting current Ix produces the flux which induces the terminal voltage E0. For a given synchronous reactance, the voltage E at the terminal of the generator depends on E0 and this Z. Now, in this type of mathematical problem situation, just remember this is a per phase representation. Per phase representation means your E0 is phase voltage, E is phase voltage, I is also phase, but because this is Y connected, phase and line is the same. So just remember this part, that E0 and E, they are phase voltage, that is fine, but they may say that I is the line current. Because this is Y, this is coming from Y, so line and phase should be the same. But I is line actually here. I is the line current. If you look at here, you see that your I is actually what you draw in this circuit. This is per phase circuit. Your I was line current. Now, can we solve a problem related to this discussion now? Equivalent circuit of a synchronous machine. This is per phase equivalent circuit. We will take a break after this. A three-phase synchronous generator producing an open circuit line-to-line voltage 6928 volt when the DC exciting current is 50 ampere. The AC terminals are then short-circuited, and the three line currents are found to be 800 ampere. AC terminals are short-circuited. Okay. Calculate the synchronous reactance per phase. And then calculate the terminal voltage if three 12 ohm resistors are connected in Y across the terminals. Who can do A of this, or B, or both? Is anyone trying to do this, or not at all? Anyone is trying? No? Let's try together. Have you done the question? Good. So, we need a light. Yes. Now, where are we? We are sort of here. The first part, it is saying that three-phase synchronous generator and produces an open circuit line-to-line voltage 6928. This is line-to-line. This is line-to-line voltage. So this is the voltage generation here. And the DC exciting current is 50 ampere. Here IDC is 50 ampere. Anyway, that is given. That is good information. We will not use it anyway. Then the AC terminals are then short-circuited, and the three-phase line current are found to be 800 ampere. So what it says in the given condition, that your AC terminal that has been short-circuited. So here it is short-circuit. Now from the equivalent circuit of the synchronous machine, we know that we have a voltage source, we have synchronous reactance, we have load if that is connected there. Now if this is short-circuit, then there is no load. And when it is short-circuited, they said that the current which was flowing through this short circuit, that is 800 ampere. So if there is a short circuit, 800 ampere current flowing through this way, we can see there is a current, there is an impedance, and there is a voltage. So what is the value of your synchronous reactance there? Your E0 That is actually straight away your I multiplied by XS. So your I is already given. So you have to determine your XS, that is E naught over I. Am I right? And your E naught is 6928 divided by root 3, because that is given line to line. And in this calculation, this is phase, per phase circuit. And then your I is 800 ampere. So how much is your excess? That is 5 ohm. Have anyone got it? I should give you a Kit Kat. So that is 5 ohm, the value of the synchronous reactance. You can see this is actually sort of, you are solving a simple circuit. There is nothing to do with the synchronous machine. Just you need to draw the equivalent circuit, right? So the equivalent circuit of the synchronous machine, E naught, XS, then short circuited. When you short circuit it, 800 ampere current flows through this. When your circuit becomes like that, you can write the equation. E naught, I, XS, and get the value of the synchronous reactance in this case. Now in the second part, this is actually A. Then in B, it was saying that if they connect, because you don't have a copy, you may not sure about the question. So in the second part, it was saying that you have to calculate the terminal voltage if 3 12 ohm resistors are connected in Y across the terminals. So our generator, Y connected generator, and 3-phase Y connected load is there, each 12 ohm. Because we are considering per phase circuit, so we just consider one 12 ohm resistance. And in that case, what will be the terminal voltage? That is the question, okay? Just in case. So calculate the terminal voltage if 12 ohm is connected at the terminal. Because this is 3-phase, so there will be 3 12 ohm. Now, if you want to draw your circuit, now it will look like this. That you have connected a 12 ohm load resistance. What we are looking for now, that is, what is the value of load voltage here? We are interested about that. By the time we know that our XS is 5 ohm, what is the value of I? We don't know yet, because I we determined that that was for short circuit. Once you put a load there, that will not be true. The current will be different because the resistance changes. So we don't know the I. We have to determine E, but we know E naught. That is 6928 divided by root 3, which is actually 4000 volt. In this circuit, we can write this equation that E naught equal I and Z. Z means the combination of these two, total impedance of the circuit. and we will have our I, that is E naught over Z, that is 4000 over Z is root over R square plus X square, 12 square plus 5 square. Which is giving us 308 ampere. This part becomes 13. So this is the current now. When you have synchronous reactance and a resistance in series with that. Now we need our E, that is actually your I, 308, multiplied by the resistance 12, because your E is across this resistance. And once you have 308, that is the current, and multiplied by 12, this gives you this phase voltage. The original voltage in the question was given line to line, so it is expected that you put your load voltage as line to line as well. So if you wish, you can multiply by root 3. That is better, because if the original value is given in line to line, it is expected that you give your results in line to line. So that gives you 6402 volt. Just in case, if you don't like to multiply by root 3, your result will be 3696. 3696. And you will lose 1 marks. Any question? I think you have done well. Wonderful. You deserve a break. Let's have a break for 5 minutes.
One method I was thinking of doing is just finding, so in order to find EEO, it would be the voltage across the inductor plus the voltage across the load. So I tried to do this method, but I think I got a different answer. So my step was...
Do you know the current?
So
800, 300 ampere.
Yeah.
Yeah, this is the right current.
Yeah.
Because without the current, how can you get the voltage drop across this? Do you understand what I mean?
Yeah. So I did try and apply that into this equation. So the voltage across the load would be the source.
This voltage minus this.
Yeah.
Yeah.
So it'd be I times 5.
Yeah.
And I tried to do that, but I got a different voltage.
What did you do?
I'll calculate it again.
Yep.
When I first do this, I think it's because I didn't. Wait, no, I don't think it matters if I times the square root of 3 because that's already done.
No, in this phase.
Yeah, so it would be.
You will get 3696? What is your answer? 3696? Cannot be. Something is wrong somewhere.
Yeah, I'm not sure, but I'm not. Then I'm not sure.
So the voltage across here is 4000 volt.
Yeah.
That is fine. Minus 308 multiplied by 5.
Yeah.
How much is this?
That's 1,540.
Is there some... $1,540, and so that will be 2,600.
Yeah. And then the way you do
So how much is this? 12 multiplied by 308. How much is this? 3696. Because you have 12 ohm there, isn't it?
yeah.
So, and this should be. You have to ask something.
Yeah, I've got a question, but I just realized I'm not.
Yes. So plus 5 multiplied by 308, is it?
And that should be the
But that is not coming like that. Yeah, solve this puzzle. Why it is not? Because that should be straightforward. That should not be. Should that drop and that drop should give you this.
yeah.
Huh?
Could it be because
No, there is not much science here. This voltage drop should be equal to this.
yeah, I just don't know why it's not giving the same.
Okay. Keep trying it. I will see as well. Yeah. No, that's fine.
With the extension mid-semester test yesterday, in the first question, I didn't know how to find Q or PS because you only gave me volt and
So,
current across the resistor and the current across the inductance. I just want to know how to do it. It's been like playing in my mind.
it's okay. So, by next week, I think you will get the answer and feedback as well.
Okay.
So, I think maybe you wait up to that. I forgot actually what parameters are given. But if you need that urgently, just in case, you can send an email to one. Is that okay?
Yeah, no, sorry.
This is a requirement for that class.
So we start from E. Resistance.
And there's a fraction where it's cold as well. I don't know if it's Chinese, but it might be in there. I don't know. The one thing is different, and the same thing with the don't hit your one time.
I've got this DC machine that I broke out of a blender, and with the commutators, so there's black spots. I was supplying it with a DC voltage, and then I'd take the supply off, it would rotate and it would form, the brushes would fall towards the black spot, and it would no longer rotate. So I was wondering, like, is that looked at further in other courses where, in like blenders or something, how they combat that? How they get around that? Is that just this one DC machine is full?
I have not much idea about any further courses or anything. There are two persons you can speak to because I'm mainly working in power systems, less on the machine side. Nuantha, ask him, and Brendan Megger. Have you met him? Brendan? Because he is actually sort of expert in machines.
electronics, if you can say I've done electrical, I see that as more sort of, yes, it's pigeonholed a little bit, so you won't be able to do it in the electronic space. But if you go so like, while you limit your job possibilities, you also heighten the ones that are still low. So it's sort of manufacturing design, my old job, I used to build project controllers. That's why circuit breakers and stuff are always technology. I had to fly through the ladder without struggling with exams. I've got an exemption for myself because I'm not very much job.
The last letter you get out with the high area. Yeah, now it's so simple. And all it is just you just got to represent what you got and explain why. I think from memory, I think when I did it the first time, because I did it the first time, but then I didn't realise it was happening. So when I read on these calls, I got an exemption this time. I should have got an exemption this time. No, just go past it. So the percentage deviates. The only thing is, what I'm worried about is if total marks don't count, doesn't that mean that it's hard to do to me? I don't know how that works. Yeah, I think I just get 10 out of 10. That's just what I'm because I got 10 out of 10 when I did the first one. Yeah, I'm getting an 8 average. Every time 10. Yeah. I got a 9 out of 10 from like a cool. I cried up. Then I looked at the actual mark. There was a bit where spread out. And you can use one whole mark just for as a teacher. Just for a teacher, you get me 1 mark less. I did every mark I can get going to the exam, but I struggle with exams. My mind just goes blank.
Can we start again? Good. Now there is our last topic remains, that is the phasor diagram. Happy?
Yeah, just phasor diagrams.
You are good at phasor diagram?
No, I'm not.
So let's try to do something. As I have mentioned that by marking 161 mid-semester test scripts, I'm sorry to see the performance in phasor diagram. Most of the people didn't answer at all. Whoever tried was not right. So let's try to improve that situation. And that is possible. Phasor diagram is easy. Students don't perform well because they don't practice. Usually this is at the end of the chapter, at the end of the lecture, so they don't care that much. That is the only reason. But phasor diagram is important, and usually in the exams you will be asked to draw, so let's have some lower hanging fruits. Some good marks. Okay? Now, so we have a circuit diagram, per phase equivalent circuit diagram given. per phase equivalent circuit diagram of a synchronous machine, internal generator voltage, synchronous reactance, and a load, resistance R. Now for that circuit, we can write these equations. Even we solved mathematical problems by writing these equations. These are easy. There is nothing to do with electrical plant or synchronous machine. You have learned this in your first year in circuit theory. That your voltage E naught, that will be your terminal voltage E plus the voltage drop in the synchronous reactance. And your voltage drop E, terminal voltage, that is actually IR. So these two equations is coming from your circuit theory knowledge. So let's write some equations. So the equations we have written from the equivalent circuit there are two equations. One is our E naught, that is the terminal voltage plus the voltage drop across the synchronous reactance. And our voltage at the terminal is current flowing through this and the resistance of that. So if we are asked to draw a phasor diagram just for this, how that will look like? We are taking E voltage as our reference. Okay, so this is our reference voltage. Reference voltage means you place them horizontally at 0 degree. So this is your voltage. Now, this is here, terminal voltage, isn't it? If we want to draw I for the resistive load, because this is resistance, my load is resistance, it doesn't give me any phase shift. So if I want to draw I, the magnitude of I will draw here, that this is my I. Because there is no phase shift between E and I because of R. So my I will be there. Now from this, we can see that I have I have to draw IXS. I have I, now I have to multiply XS with this I. Now XS, that is, we know that is inductance, and a pure inductance. A pure inductance is giving 90 degree phase shift. Am I right? So if I is this way, your IXS will be 90 degree with that. IXS. Why I am putting it here? Because I have to add IXS with E. So with E, I added IXS. And because of that J, there is 90 degree phase shift. So once I have my E plus JIXS, E plus JIXS, if I connect these two terminals from starting to bottom, so this is the vector summation of these two. And that gives me E naught. Any confusion here? Good. That is better. So again, we start by selecting a reference. In this case, or in case of all synchronous machine equivalent circuit diagram, our reference will be E. We draw our E. Then we need IXS to add with that. To get IXS, we have I, we multiply I XS, and we get the angle of that. And that angle is purely 90 degree, because that is pure inductance. So we have E, and then JIXS is 90 degree to that. And then we have two vectors there. We add the starting and the end point. Then this gives us the resultant vector, or the summation of these two, which is E0. This is done. Fantastic. Well done. Now, we are moving to the next part. If my load is pure inductance, not resistance, my load is pure inductor, what will happen? So in that case, I have my E as before, up to this reference, fine. Now I have I, and when that is inductance, that is not L. We say it actually IXL, isn't it? The impedance of that. XL. Instead of R, that is XL. Okay. If you have pure inductance, what will happen? So if I have E and I have inductor, so it is not IR anymore, it is IXL, inductive reactance. If my E is this, what will happen to I? Previously, it was same because resistance doesn't give any phase difference. But this inductor, how much, if it is pure inductor, how much phase difference it is giving? 90 degree. Leading or lagging? Lagging. In that case, if my E is this way, my I will be 90 degree lagging here. So this is my I in this circuit because of pure inductance. So my equation remains the same. My equation is E0 equal E plus J I XS. Previously this E was I R. Now this E is I XS, isn't it? Oh, sorry, XL. XL. Yes, this one is XL. Okay. So I have my E. Now, according to this equation, I have to add this IXS with this E. I have to add IXS with this E. If I have I, so this is my I, this way. If I want to draw IXS, what will happen to that? You can't see. Sorry. So this is my I in this circuit. Now IXS, that will be 90 degree phase shift with this I, same as before. So if this is I, your IXS will be 90 degree phase shift with I, is it? So if I want to draw my IXS, that will be this amount, isn't it? That will have a 90 degree with I. Same as here. I and IXS is 90 degree. So this IXS have 90 degree phase shift with I because of the XS. According to our phasor diagram or this equation, I have my E, then I have to add this IXS with this E, isn't it? So this one will actually appear here. Do you understand what I am doing this part? IXS? Because I want to get this equation. I have my E and I am adding IXS to this E. Why I am drawing it here? Just to show that I and IXS has 90-degree phase shift. Okay? So in the phasor diagram, you don't draw it here, you draw it there. So what will be your E naught now? Your E naught will be your E plus IXS. Why the shape of this? Because of this inductive load here. Is it okay or a little bit of confusion? The resistive one was easier than here because you have 90-degree phase shift and you have to put now two phase shifts. One for the load inductance, another one for the synchronous reactance. Let's try one more. Let's try one more. That is, our load is capacitive. If our load is capacitive, our terminal voltage E is IXC. Now our E is reference. Here, this is E. Because of the capacitance, there is 90-degree phase shift, and that is leading. So the angle between this E and I will be 90 degree. So this is my I, load current now, due to XC. This is my current I due to XC now. Then our equation says that our E naught will be E plus JIXS. This is for load. That's what we have drawn here. This one
Plus
XS, because this is coming from the basic equation, and this E is IXC. XS remains as it is there, because that is coming from the synchronous reactance of the circuit, and this is coming for the changing in the load. So if this is I, what will be my IXC? You remember IXL was this way? So IXC will be here. This will be my IXC. But like before, we don't draw it here, because in the equation you have to draw, it is actually this one. You have to draw it here, IXS. Then your total E naught, that will be from here to here. So as you can see in the capacitive circuit, your resultant voltage is actually lower than that due to the capacitive effect. So these are three phasor diagrams considering resistive load, considering inductive load, and considering capacitive load. Let's revise it again here. So we have our per phase equivalent circuit, and in the per phase equivalent circuit we have our internal generator resistor, internal voltage, synchronous reactance, and the terminal voltage. And we know that our terminal voltage and the voltage drop gives us the internal voltage. And the terminal voltage, it is actually load voltage, so current multiplied by the resistance. So how to draw this? We actually draw this equation. Our terminal voltage E, that is our reference. Then we add IXS with that. To draw IXS, there are two components. One is I and XS. So we have to get the angle of I and XS. Angle of I will be the same as angle of E because of this resistance there is no phase shift. So I is in this way. Now what will be the direction of IXS? Because XS is pure inductance, that will give a 90-degree phase shift. So you draw your IXS with perpendicular to this E. And from this equation, once you draw your E and you have your IXS, once you add them together, that is giving you the total voltage E naught. The angle you see between E and E naught, this angle is called torque angle for a machine. The angle between the terminal voltage of the machine at the load terminal and the internal voltage E naught. So the angle between E naught and E, this is the angle. You can see this is E, that is E naught. This angle delta is called torque angle of the synchronous machine. Torque angle of the synchronous machine. So we have drawn actually these three. The phasor diagram. This one, resistive one, what we have drawn in the previous page, it is the same. But instead of your horizontal E, it is written as VT and it has been drawn this way. But this resistive one is the same as this one. Why I put this? You have some study materials for this course, isn't it? There is some. So in that material actually this diagram has been given. So I haven't changed it. But we have drawn these three for inductive, resistive and capacitive. The angle theta you see, that is the power factor of the external conductor impedance. That theta is coming for the load. And this delta, that is actually we got at the end. Once we complete the diagram, you find the angle between E and E naught, that is delta. And theta is coming from the load, depending on whether the load is resistive, inductive, capacitive. Practically, they are not purely inductive, not purely capacitive, not purely. So there is a phase shift. That's why you will see some angle theta there. Whatever we have considered here, you see that we have considered pure resistive, pure inductive and pure capacitive. But in practical load, there will have some angle. So your I will not be aligned with E, your I will not be perpendicular, 90 degree here or 90 degree there. What will happen in that case? So what will happen? Can you see anything? No. What I am showing you, you can't see actually. So what I was saying, that what we have drawn here, that your E and I in the same, means pure resistive. Your E and I has 90 degree phase shift, pure inductive. Your E and I has 90 degree phase shift, pure capacitive. Practically, it will not be like that. Depending on the load, combination Rx, Rc, you will have a power factor of your load. So, if you have a power factor in your load, you have your E there, your I will not be here, not be straight down, not be straight up. Your I will have a certain angle with your voltage. it is actually if your E equal IZ, not IR, not IXC, not IXL, IZ. Then for this load you will have a particular power factor angle theta. What is happening in this world today? It is focusing my hand, which is less important than the numbers. Can you see something? Okay, it is better now. So our load angle will have a certain angle because that is a combination of resistance, inductance and capacitance. So if that angle is theta, what will happen? And you expect to see this type of question in the exam, not pure resistance, not capacitance, not inductance. Okay. Now this is your terminal voltage and you have an angle theta of current due to that voltage. So there is an angle difference between your terminal voltage and terminal current.